Hello and welcome everybody to another episode of Books in Bytes. Today we're diving deep into Stephen Hawking's A Brief History of Time. It's a book that sold over 10 million copies and been translated into more than 40 languages. Now that's pretty impressive for a book about, well, the universe.
It really is. It's not just about the numbers. It's Hawking's ability to take these complex ideas, like the Big Bang, black holes, and the nature of time itself, and make them understandable, even for those of us who aren't physicists.
Exactly. He guides us through our understanding of the universe, from the ancient Greeks to the present, tackling these big questions about how it all began, where it's going, and the forces that govern it. It's a journey that spans centuries of thought and discovery, and we're going to unpack it all right here.
That's right. So let's begin our deep dive at the beginning with those early models of the universe. Hawking starts with the ancient Greeks, who, despite limited technology, made some surprisingly accurate deductions.
Yeah, it always amazes me how they figured out the Earth was round, just by observing ships disappearing hull first over the horizon.
Yeah.
It's a simple observation. But it speaks volumes about their powers of deduction.
It does. But what's fascinating is how, despite understanding the Earth's shape, they held on to this geocentric model for centuries. This model, championed by Aristotle and Ptolemy, placed the Earth at the center of the universe, with the sun, moon, stars, and planets revolving around it in perfect spheres.
It seems so counterintuitive to us now, but their model did a pretty good job of predicting planetary movements for the time.
It did, to a certain extent. But there were some inconsistencies they just couldn't reconcile, like the apparent changes in the size of the moon. Ptolemy tried to explain it away with these complicated epicycles, but ultimately his model couldn't fully account for these observations.
And that's where Copernicus enters the scene, right? He was the one who dared to challenge the established view and put the sun at the center of the solar system. It was quite the revolution in thinking back then.
It absolutely was. Copernicus's heliocentric model wasn't just a shift in perspective, it was a complete upheaval of the established worldview. It took nearly a century for his ideas to gain widespread acceptance, facing strong opposition from religious authorities, who saw it as a threat to their doctrines.
Speaking of challenging established views, we can't forget Galileo. He was a champion of observation and experimentation, and his work paved the way for modern physics. It's ironic how his observations of Jupiter's moons, which supported the heliocentric model, landed him in hot water with the Catholic Church.
His struggle highlights a key theme that runs throughout A Brief History of Time: the tension between scientific progress and dogma. Galileo's insistence on trusting the evidence, even when it contradicted long-held beliefs, is a cornerstone of the scientific method.
And then comes Newton, who took Galileo's work and ran with it, developing his laws of motion and universal gravitation. These laws weren't just abstract theories. They provided a practical framework for understanding how objects move and interact.
That's right. Newton's work was a watershed moment in science. His laws explained everything from the falling of an apple to the orbits of planets, laying the groundwork for a mechanistic view of the universe that would dominate scientific thinking for centuries.
He even dabbled in alchemy and biblical prophecy later in life. It seems like even the greatest minds have their quirks.
They certainly do. But what's fascinating about Newton is how his work, despite its immense influence, eventually gave way to an even more revolutionary theory: Einstein's theory of relativity.
Yeah, Einstein. He completely changed our understanding of space, time, and gravity with his theories of special and general relativity.
What's crucial to understand is that Einstein didn't just replace Newton's laws. He showed that they were a special case, applicable in most everyday situations, but breaking down when dealing with very high speeds or very strong gravitational fields. That's where relativity comes in.
Right, so tell me, what was so groundbreaking about special relativity?
Well, imagine you're chasing a beam of light, no matter how fast you go. The light will always seem to be traveling away from you at the speed of light. That's because the speed of light is constant, unlike anything else we experience in everyday life.
Okay. I think I'm starting to see where this is going.
Exactly. Einstein realized that to make sense of this, our notions of space and time couldn't be absolute. They had to be relative to the observer. That's the core insight of special relativity. Time slows down, lengths contract, and mass increases as you approach the speed of light. It's completely counterintuitive, but has been confirmed by numerous experiments.
And then general relativity takes us even further, right? It's not just about motion. It's about gravity and its effect on the very fabric of space-time.
Right. General relativity explains gravity not as a force, but as a curvature of space-time, caused by the presence of mass and energy. Think of a bowling ball on a trampoline. The ball creates a dip in the fabric, and that's analogous to how massive objects warp the fabric of space-time.
So the Earth isn't really attracted to the sun. It's just following the curvature of space-time created by the sun's massive presence. It's such a mind-bending concept. But it explains so much, like the bending of light around massive objects.
Exactly. And one of the most compelling pieces of evidence for general relativity came in 1919, when astronomers observed the bending of starlight around the sun during a solar eclipse. This confirmed Einstein's prediction and cemented general relativity as a cornerstone of modern physics.
These theories seem so abstract and complex. But they're more than just equations on a blackboard. They've led to incredible technologies, like GPS, which relies on the principles of relativity to function accurately.
You're right. It's a great example of how seemingly esoteric scientific theories can have real-world applications that affect our daily lives.
So we've journeyed from a universe centered around the Earth to one governed by universal laws of motion and gravitation, and finally to a universe where space and time are relative, and gravity warps the fabric of reality. It's been a wild ride.
It has. But the journey doesn't stop there. From here, Hawking takes us into the realm of cosmology, where we explore the origins and evolution of the universe itself.
Ah, yes, we're finally getting to the Big Bang. I'm ready to have my mind blown.
Well, get ready, because things are about to get really interesting. Welcome back to our deep dive into Stephen Hawking's A Brief History of Time. We left off on the cusp of the Big Bang, ready to explore the origins and evolution of the universe.
You know, the idea that the universe had a beginning, that it wasn't always there, is just mind-boggling. How did we even come to accept this theory? It seems so counterintuitive.
It's a journey of discovery that spans centuries. In A Brief History of Time, Hawking guides us through the evidence. That led to the widespread acceptance of the Big Bang theory.
So where do we start?
Well, one of the key pieces of evidence comes from the work of Edwin Hubble in the 1920s. Hubble observed that distant galaxies are moving away from us, and the farther away they are, the faster they're receding.
So the universe isn't static. It's actually expanding.
Precisely. And this expansion implies that at some point in the past, everything must have been much closer together, perhaps even concentrated at a single point.
Okay, I'm starting to see how this leads to the Big Bang. But isn't there another theory? The steady state theory that tried to explain the expansion without a beginning.
There was. The steady-state theory proposed that the universe had always existed, and that new matter was continuously being created to maintain a constant density as the universe expanded. But this theory ran into problems when astronomers discovered the cosmic microwave background radiation.
Ah, yes. The cosmic microwave background. That faint afterglow of the Big Bang itself is like the universe's baby picture, right?
Exactly. The cosmic microwave background radiation is a faint, uniform glow of microwaves coming from all directions in space. It's the remnant heat from the Big Bang, cooled and stretched by the expansion of the universe over billions of years.
It's amazing to think that we can actually detect this relic of the universe's earliest moments. But even with all this evidence, the idea of a universe with a definite beginning raises some profound questions.
It does. Questions about what caused the Big Bang, what existed before it, and even what it means for our understanding of time itself.
Right. If the universe began with the Big Bang, was there even a before? What does it mean for time to have a starting point?
Those are questions that have puzzled physicists and philosophers for decades. Hawking himself explores these questions in A Brief History of Time, delving into the nature of time and how our understanding of it is shaped by the Big Bang theory.
So let's talk about time then. It seems like such a straightforward concept, always moving forward, never stopping. But in A Brief History of Time, Hawking presents a much more nuanced view of time, doesn't he?
He does. He introduces the concept of the arrow of time, the idea that time flows in one direction. From past to future, we experience this arrow of time in everyday life. Eggs break, but they don't unbreak. We remember the past, but not the future.
It seems so obvious, so fundamental to our experience. But is there a physical explanation for why time flows in only one direction?
That's a question that has puzzled physicists for centuries. The laws of physics at a fundamental level are time symmetric, meaning they work equally well whether time is moving forward or backward. Yet our experience of time is clearly asymmetrical.
Okay, that's confusing. If the laws of physics don't distinguish between past and future, why do we experience time moving in only one direction?
Well, Hawking proposes that there are actually different arrows of time that contribute to our perception of time's directionality. There's the thermodynamic arrow of time, linked to the second law of thermodynamics, which states that entropy, or disorder, tends to increase over time in a closed system.
So the universe is constantly becoming more disordered, and that's why we perceive time moving forward.
That's one way to think about it. Then there's the psychological arrow of time, based on our perception of time and our ability to remember the past but not the future.
So our experience of time is shaped by both the physical laws governing the universe and our own mental processes.
That's right. And there's also the cosmological arrow of time, tied to the expansion of the universe. As the universe expands, it becomes less dense and cooler, providing a clear directionality to time.
This is all starting to make sense, but it's still mind-boggling. In the book, Hawking talks about the possibility of time travel, both forward and backward. Is that even scientifically plausible?
Hawking explores the theoretical possibilities of time travel, but he also points out the immense scientific hurdles that would need to be overcome.
Like what?
Well, for starters, to travel back in time, you would need to create a wormhole, a theoretical tunnel through space-time, even if we could create such a thing, which is highly speculative. There's the issue of causality.
Causality, what do you mean?
I mean, if you could travel back in time, you could potentially change the past, creating paradoxes. For example, you could go back and prevent your own birth, which logically shouldn't be possible.
I see. So time travel, at least to the past, might be inherently paradoxical.
That's one interpretation. Hawking also proposes another intriguing possibility. He suggests that the past might be fixed, having already been observed. While the future is open and subject to quantum uncertainty, this would mean that time travel, if possible, might only be possible to the future.
Fascinating. So while we haven't cracked the code on time travel just yet, a brief history of time encourages us to think about the nature of time in a whole new way, challenging our assumptions about its linearity and immutability.
Absolutely. And from our exploration of the universe's beginning and the nature of time, Hawking takes us on a deep dive into one of the most enigmatic and captivating phenomena in the cosmos: black holes.
Black holes. Now, those are truly mind-blowing objects, regions of space-time where gravity is so strong
Yeah.
that nothing, not even light, can escape.
Precisely. And Hawking has made significant contributions to our understanding of these cosmic monsters.
I remember reading the chapter on black holes and feeling a mix of awe and terror. The idea of being stretched and squeezed like spaghetti as you fall into a black hole, that's some pretty intense imagery.
It is. Hawking doesn't shy away from describing the rather gruesome effects of a black hole's immense gravitational pull. But beyond the terrifying aspects, black holes offer profound insights into the nature of gravity and the limits of our understanding of physics.
So tell me, how do black holes even form?
Well, they form when massive stars, much more massive than our sun, exhaust their nuclear fuel and can no longer support themselves against their own gravity.
So the star collapses in on itself.
Exactly. The core of the star implodes, becoming increasingly dense until it collapses into a singularity, a point of infinite density surrounded by an event horizon.
The event horizon. That's the point of no return, right? Once you cross it, there's no escaping the black hole's gravitational pull.
That's right. Not even light can escape from within the event horizon. It's a boundary in space-time, beyond which our current laws of physics break down.
This raises so many questions. What happens inside a black hole? Does time even exist there?
These are questions that physicists are still grappling with. Hawking himself devoted much of his research to understanding the mysteries of black holes, and he made some groundbreaking discoveries.
Like what? Tell me more.
Well, one of his most significant contributions was the discovery of Hawking radiation. This theory proposes that black holes aren't entirely black after all.
Wait, I thought nothing could escape a black hole.
That's what classical physics would suggest. But Hawking, drawing on the principles of quantum mechanics, showed that black holes can actually emit particles, now known as Hawking radiation.
Okay, this is where my brain starts to melt.
Yeah.
So black holes, these ultimate cosmic prisons, can actually leak radiation. How does that even work?
It's a complex concept that involves the interplay of quantum mechanics and general relativity. Essentially, virtual particle pairs are constantly popping in and out of existence near the event horizon. Normally, these particles annihilate each other almost instantly, but at the event horizon, one particle can fall into the black hole, while the other escapes as Hawking radiation.
So it's like the black hole is slowly evaporating.
Exactly. Hawking radiation causes black holes to lose mass over incredibly long timescales. It's a phenomenon that has profound implications for our understanding of black holes and the nature of space-time itself.
This is all so mind-bending. But it's also incredibly exciting to think about these mysteries that are still waiting to be solved.
It is. And Hawking's work on black holes highlights another key theme in A Brief History of Time: the search for a unified theory of physics that can reconcile general relativity with quantum mechanics.
Right. We've been dancing around this idea of a unified theory throughout our deep dive. It's the holy grail of physics, isn't it? A single theory that could explain all the forces of nature, from the smallest subatomic particles to the largest structures in the universe.
Exactly. And while we haven't found that elusive theory yet, Hawking points to some promising candidates, like string theory, which attempts to unify gravity with the other forces by proposing that the universe is made up of tiny, vibrating strings.
Okay, so we've explored the Big Bang, the nature of time, the mind-boggling world of black holes, and now we're on the verge of delving into the quest for a unified theory. I'm sensing a grand finale coming up.
You're right. In the final part of our deep dive, we'll explore the ongoing search for a unified theory and its implications for our understanding of the universe and our place within it.
Welcome back to our deep dive into Stephen Hawking's A Brief History of Time. It's amazing how much ground we've covered, from the Big Bang to black holes. But there's one final unifying theme we need to explore: the search for a theory of everything.
You're right. This is the ultimate goal of physics: to find a single, elegant framework that can explain all the forces of nature and the behavior of matter, from the smallest subatomic particles to the largest structures in the universe.
It's a quest that has driven physicists for centuries, hasn't it?
It has. And while we haven't reached the finish line yet, A Brief History of Time gives us a glimpse into the progress we've made and the challenges that lie ahead.
So where do we stand in this quest for a theory of everything? What are some of the key breakthroughs and obstacles?
Well, one of the biggest hurdles is unifying gravity with the other three fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force.
Right. Those two puzzle pieces we've been talking about. General relativity for gravity and quantum mechanics for the other forces, they just don't seem to fit together.
Exactly. General relativity describes gravity as a curvature of space-time caused by mass and energy, while quantum mechanics describes the behavior of matter and energy at the atomic and subatomic levels. They're both incredibly successful theories in their respective domains, but they're based on fundamentally different principles.
So how do you reconcile a theory that describes the universe on the grandest scale with one that governs the microscopic world?
That's the million-dollar question, and it's a question that has led to some incredibly creative and mind-bending theories.
Like string theory. That's the one that proposes that everything is made up of tiny vibrating strings, right?
That's right. String theory, and its more encompassing cousin M theory, are among the leading contenders for a theory of everything. They suggest that the fundamental building blocks of the universe aren't point-like particles, but tiny one-dimensional strings. The different vibrations of these strings give rise to the different forces and particles we observe.
So gravity, electromagnetism, and the nuclear forces are all just different notes played on these cosmic strings. That's pretty wild.
It is. And what's even more intriguing is that string theory requires extra spatial dimensions, beyond the three we experience. These extra dimensions are curled up so small that we can't perceive them directly, but they play a crucial role in the theory.
Extra dimensions. Vibrating strings, it's all so far out there. But there's a certain elegance to it.
There is. And while string theory is still highly speculative and difficult to test experimentally, it offers a tantalizing glimpse into a possible unified description of the universe.
But even if we were to find a complete unified theory, would it be the end of physics? Would we finally have all the answers?
Hawking doesn't think so. In A Brief History of Time, he argues that even with a theory of everything, there would still be countless questions to ask and mysteries to unravel. For example, a theory of everything wouldn't necessarily tell us why the universe exists, or why the laws of physics are the way they are.
So it wouldn't be the end, but rather the beginning of a whole new chapter in our understanding of the universe.
Exactly. The quest for knowledge is an ongoing process. A theory of everything wouldn't close the book on physics. It would simply open up new avenues of exploration, leading us to even deeper and more profound questions.
You know, one of the things that struck me most about A Brief History of Time is Hawking's unwavering optimism. He acknowledges the immensity of the challenges we face in understanding the universe, but he never loses sight of the incredible progress we've made and the potential for future discoveries.
You're right. He writes, We are just an advanced breed of monkeys on a minor planet of a very average star, but we can understand the universe. That makes us something very special. It's a powerful message, one that reminds us that despite our smallness and the grand scheme of things, we have the capacity to grasp the universe's secrets.
Absolutely. And as we wrap up our deep dive into a brief history of time, I think it's important to remember that this book isn't just about abstract theories and complex equations. It's about our place in the universe, about the wonder and awe we feel when we contemplate the vastness of space and time.
Well said. Hawking's book is a testament to the power of the human mind, to explore, to question, and to seek understanding, and it leaves us with a profound sense of possibility, a sense that even the most fundamental mysteries of the universe might one day be within our grasp.
And on that note, I think it's time for us to step back from the cosmos and let our listeners ponder the mysteries we've explored. If you've been captivated by this deep dive, I encourage you to pick up a copy of The Unillist, A Brief History of Time, and delve deeper into the wonders it holds. You might just find yourself looking at the universe and our place within it with a newfound sense of wonder and appreciation.
And who knows? Maybe one of you listening will be the one to discover the elusive theory of everything. Until then, keep those minds curious and keep exploring the universe around us.
Well said. Thanks for joining us on this incredible journey through Stephen Hawking's masterpiece. Until next time, keep those brains buzzing.